at least one of them should be true. If all are false, among all one should be true. Then that is a contingency. Okay. Then tautology means all are true. A contradiction means all are false. Okay. Then what do you mean by equivalent statement? Then what is the condition so that you can say that two compound proposition will be equivalent to each other? Yeah, Snehajit, tell.
Sir, when two compound proposition always have the same truth value,
Yeah.
Regardless of what the truth value is.
So that means whatever all the possible cases or all the possible assignments of truth values of the proportional value PQ, whatever the PQ are, for all possible cases, the truth table or truth column of both the compound proposition identical or same truth values, then you can say that they are equivalent to each other. Okay, good.
Yes.
Okay, now today we will see some more about logical equivalences. Okay. 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 This we have given some examples in the last class that equivalence, congruence, equivalence statements. Okay. And some of the trivial examples are that the conditional statement is contrapositive, converse and inverse. There are some trivial examples. Okay, will some basic laws or basic or standard laws along with logical equivalences. One of them is De Morgan's law. De Morgan's law, or you may say De Morgan's laws. See, De Morgan's laws, there are De Morgan laws in case of trigonometry also. These De Morgan laws in case of propositional logic. You have to understand that. Okay. For any two given propositions, P and Q. That means P and Q that are the given propositions. So De Morgan's law says that if we are going to find the negation of P and Q, this will be equivalent with what? Any idea? Okay, see, negation of P conjunction Q, that will be equivalent statement to what? That
negation P union negation Q.
Yeah, negation P not union, that is disjunction or. Okay, disjunction, negation.
Sorry.
Yeah, negation P, then negation N. That means you just for understanding negation of N means not N. That means that will be or. So negation P, disjunction, negation Q. That is one of the law of De Morgan's law. Similarly, you can see negation of P disjunction Q or P or Q. That will be equivalent to what? Tell me.
Negation P and negation Q.
Yeah, negation P and negation Q. These two statements, these two equivalent statements are called De Morgan's laws. This proof is you can prove very easily. That means which can be proved or verified by using truth table. That means find the truth table of both the cases. If the truth table or truth columns for the compound proposition are same or identical, then it's a equivalent. It will be the definition. Okay, I will go through proof of one using truth table. Okay. As for requirement P and Q, that are the given propositions. As for requirement, negation P is requirement, negation Q is there. So just find negation P, negation Q, and P and Q is there. So we are going to find negation of P and Q. So first we have to find P and Q, then negation of P and Q. That is the requirement. This one, this column, and negation P, disjunction, negation Q. That is also requirement. Just you may just use the table. Okay. First case, true, 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 false, false, true, and false, false. See, I'm just going through one proof of the using the truth table. For all other proofs, you can use truth table. Okay. What will be negation P? For true, true, false, false, all the cases we have written. So that will be false, false, true, true. Negation Q. True, false, true, false. That will be false, true, false, true. Then what will be P and Q? P and Q.
False, 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 true.
How?
True,
True,
false,
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 false.
false.
Yeah, first one is both are true, then true. All are false. Yeah. Then negation of P and Q. So as P and Q is true, all are false. So negation of this previous column, that will be true, for it will be false, and all false. So that will be true. That is the negation part. Okay. Then negation P, disjunction, negation Q. See here, these two columns, negation P and negation Q. False, false. It will be
False.
false. That means at least one is true, means disjunction will be true. False, true, true, false, true, true. So at least one is true is there. So all are will true. That means see here, this column. That means what? Two compound proposition, left hand side and right hand side, to the equivalent. So this and this, see this, just observe. False, true, true, true. False, true, true, true. That means these two columns for compound proposition, this and this, are identical. So you can directly write this equivalent to this. That means you can write the truth values for negation of P conjunction Q, and that one negation P, disjunction, negation Q, that one are identical. That means thus we can conclude that negation of P conjunction Q, that must be equivalent to negation P, disjunction, negation Q. For proof of true, for our second part, you can do it by using truth table. Okay. Similarly, you find those negation of P, disjunction Q, and find negation P, conjunction, negation Q. Both will be identical. Similar truth value, same truth value. Okay, that is one of the law. See, there are some more laws or more standard laws that we can use as in some problems that are some more logical equivalences. See, according to we will take some notations. T, capital T, denotes compound proposition that is always true. The compound proposition that denotes three, capital T, that is always true. Always true means which category? It is a tautology. And let capital F denotes, just for notation, not true, false, that is a compound proposition. That is always false. Okay. Always false means which category?
Contradiction.
Yeah, that means F denotes any contradiction compound proposition. T denotes any tautology compound proposition. Okay. Then we will some standard equivalences. Then in the right hand side, name of these or laws. What it says, see, take any proposition P, conjunction with any tautology. This will equivalent to what? Any idea? P is any proposition that may be true, false. So T means tautology, all are true. So that conjunction will be,
Can be any true or false.
yeah, not any. So as T is always true. So there depends on fully true. P means if that will be same as P. P is true, false. N means when P is true, T is always true. So that will be true. When P is false, that P conjunction T is false. So that will be same as P. And P disjunction, any contradiction means always false. That will be equivalent to F is false, always false. So that depends on P. If P is true, that will be true. If P is false, that will be false. That it fully depends on P. These two laws are called identity laws. That is just for notation. These two laws. Another one is P disjunction T. Then what will be this? And P conjunction any contradiction. What will be this?
So first one will be always true.
Yeah, first one will be always true. As is disjunction, as T is always true, that will be always true. That means it will be tautology. Then P conjunction F. F means contradiction, always false. As it is always false. So both cannot be true at a time. So it will be depends on contradiction F. These laws named as domination laws. These are some standard equivalences you can use in some problems or some simplification you can use these notations. Okay. P or P disjunction P will be equivalent to what? In P conjunction P. It will be same. It will be P disjunction P. So that will be simply P conjunction P that depends upon P. These two laws are called idempotent laws. Okay. Similarly, there are more standard laws. If you want then negation of negation P. What will be this? Equivalent to? Not equal to, that will be equivalent to. Use this symbol equivalent. Negation of negation P. That will be simple P. This law is called double negation law. Also, okay. P disjunction Q. That will be equivalent to Q disjunction P. Also, P conjunction Q. That will be equivalent to same as Q conjunction P. These two laws are called which law? Just observe. P conjunction Q, that is same as or equivalent to Q conjunction P. That means the form of A plus B equal to B plus A, like this. A into B equal to B into A. Same form. It will be which law? Okay, that law is called commutative law. Commutative laws. That means you can see one law, addition is commutative, multiplication is commutative, like the same way disjunction is commutative, conjunction is commutative, like this. But conditional is not commutative. A P conditional Q, that is not same as Q conditional P, that is different. But in case of conjunction and disjunction, both are same. P conjunction Q, that is equivalent to Q conjunction Q disjunction P, same as. That means both conjunction and disjunction are commutative in propositional logic. Okay. Like this, similar laws, P disjunction Q disjunction R, that will be same as first two is bracket. If you take P disjunction Q disjunction R, that will be also both are same. P conjunction Q conjunction R, that will be also same as P conjunction Q conjunction R. These two laws are called which law? That means
Associative law.
associative law. Yeah, good. Associative laws. That means you can say conjunction as well as disjunction are associative over the proposition. Okay. Then P disjunction Q conjunction R. What will be this? This will be equivalent to what? Any idea? P disjunction over the bracket is given Q conjunction R. Okay. This will be equivalent to P disjunction Q conjunction P disjunction R. That means P disjunction Q, then end in their bracket P disjunction R. That means here disjunction is distributive over conjunction. Okay. Like the same way, P conjunction Q disjunction R. What will be this? Equivalent to what? Same way, that is the law. Conjunction is distributive over disjunction. That means P and Q disjunction P and R. These two laws are called which law?
Distributive.
Yeah, distributive law. These all are written in your book. Distributive laws. Okay. Then De Morgan law. See, I am not going through the proof. If you want the proof, just find the truth table. From the truth table, just check that both columns of these equivalent left hand side and right hand side, they are same. If you are getting same truth value, that means they are equivalent. All have getting the same columns are identical. Okay. Then P disjunction P conjunction Q, it will be equivalent to what? N. P conjunction P disjunction Q, it will be what? That is very simple. Just apply the distributive law, you will get. It will be what?
P disjunction Q conjunction
P-
P disjunction.
Yeah, P disjunction P, that is same as P, then N. P disjunction Q, that will be, so P is there. So both end is there. So that will be simply P. If you apply the distributive law, then P conjunction P disjunction Q, that will be simply also P. That means here P is absorbed. So you can write this law is called absorption law. Just name are there. Also that we have already I think that P disjunction negation P. What will be this? And P conjunction negation P. What will be this? These two property, last two property we have already proved. Examples of tautology. See it. P disjunction
First
negation.
is tautology.
Yeah.
F is second is contradiction.
Yeah, it will be always tautology, stands T, it is always false for F. These two laws are called negation laws. These are some standard naming logical equivalences. Okay. For proof, you can go through the truth table. Okay.
Sir,
Tell.
will the proofs also come along with the laws in the exam?
No, see, these are some basics. See, you can, if your proof is coming, then you can go through the truth table. See, in some cases, proof will come in. That means that we'll see what type of problems will come. Problems will come that tautology, check that it is a tautology or not, it is satisfiable or not. That problems will come. Same truth table. You all should know about the truth table. Okay, tell me one thing. I'm asking. In the distributive law or associative law, how many variables are there? How many proportional variables are there?
So 3.
Three variables are there, P, Q, R. Then tell me, when you are going to find the truth table, in that truth table, how many rows will be there? How many possible cases of P, Q, R will be there?
8.
8. Then you can find it. That means see, when only P is there, only true false. When P, Q, P may be true false, Q may be true false, then 2 into 2, that is 2 square. There will be 4 rows. For all 4 possible cases, you have to find. P, Q, R, 3 proportional variables are there. So there will be 8 possible cases. So you have to find all 8 rows, all possible cases of P, Q, R. So that is the truth table. Okay. Okay, some conditional equivalence means some equivalence statements involving some conditional. That means see, P conditional Q. Tell me, P conditional Q is equivalent to what?
Negation P or Q.
Negation P or Q. Yeah, we have already shown that negation P or Q. Already we have proved that by using truth table. You can use the previous classes. We have already proved that the same. P conditional Q is equivalent to negation P or Q. How to prove? Using truth table, you can go to the previous class. Okay. Then same P conditional Q is equivalent to what? From the standard definition. That is equivalent to its contrapositive. What is the contrapositive?
Negation Q, condition negation P.
Negation Q conditional to negation P. That means we have already seen the last class. In the contrapositive, the conditional statement and its contrapositive have the same truth values. They have same truth values. That means they are equivalent. That means P conditional Q is equivalent to that its contrapositive, that is negation Q conditional to negation P. If you want, then you go through the truth table. They will be truth value will be same. Okay. Then from this, just tell me what will be P disjunction Q. Just see the first statement. P conditional Q equivalent to negation P disjunction Q. I am asking P disjunction Q will be equivalent to, instead of negation P, it is P. So negation of negation P, that is P. So that will be
Negation P implication Q.
P conditional Q. Okay. Similarly, there are some others. P and Q equivalent to, and just use the De Morgan's laws, you can get it. Negation of P conditional to negation Q, and negation of P conditional Q, that will be equivalent to P and negation Q. That's the same thing. Instead of negation Q, just Q. That will be same thing. Also, okay, P conditional Q and P conditional R, this will be equivalent to what? Any idea? P conditional to Q, that means if P then Q, and if P then R, and is there, then what will be the equivalent to what? Okay, that will be P
P
conditional to Q and R. Q and R. Similarly, if you write P conditional to R, conjunction Q conditional to R, that means see, just different. The last part is same. That means if P then R, and if Q also then R, then what will be this equivalent to? Just think, you can get it. If P then R, And if Q then R, that will be equivalent to what?
Sir, R conditional P and Q.
Now see, if P then R, if Q then R, so conditional to R will be there. That means conditional to R will be there. Then what will be this? It may be P,
P and
it may
Q.
be Q, not P and Q. P and Q means both will be there. It may be P, it may be Q. P digital
Okay.
conjunction Q. That means if P, then also R. If also Q, then also R. Okay. P conditional Q, disjunction P conditional R. That will be equivalent to what? Same. P conditional Q. If P then R or P conditional to R. That is simple. P conditional to Q disjunction R. Similarly, there is another one. P conditional R disjunction Q conditional R. That will be equivalent to what? P conjunction Q conditional to R. See, all these equivalences you can use truth table for the proof or the verification or demonstration. For all these logical equivalences. Okay. There are some logical equivalences using biconditional equivalences. That means some logical equivalences using biconditional connector. Okay. P biconditional Q, that will be equivalent to what? From the definition, you can get at least one. What will be this? What is biconditional sense? If P then Q and if Q then P. From the definition, you can get it. If P then Q and if Q then P. That will be also equivalent statement of P biconditional Q. Okay. There are some others also. P biconditional Q, that will be equivalent to negation P biconditional to negation Q. If you find the truth table, both will be same. P biconditional Q, that will be also equivalent to P conjunction Q disjunction negation P and negation Q. Negation of P biconditional Q, that will be also equivalent to P biconditional negation Q. These are some known logical equivalences using biconditional logical operator. Okay. See, for the proof, if you want, just go through the find the truth table and just compare the two columns. If they will be same. Okay. Well formed formula, or it is short form is WFF. Well formed formula, that means see. That means see, as we have already studied that order of precedence. Okay. That means there is a standard way to write the logical expression or propositional expression. So if it is not written in a well organized form, then that will be not a well formed formula. If it is written or it is understanding everything in the bracketed and the connectives are in the proper way, then it will be a well formed formula. Okay, we'll see. Every atomic propositions are well formed formulas or WFF. Why it is a well-formed formula every atomic proposition? See, every atomic proposition means this proposition that cannot be simplified further, or no connectives will be there. So that are single proposition. So that are by default they are well-formed formula. Nothing to change. Okay. If P and Q are well-formed formulas, see, that means P is a well-formed formula and Q is a well-formed formula. You can use any of the connectives you know to P and Q. That will be also well-formed formula. That means we know that one connector is negation, so negation P. You can use negation Q. You can use any of the connector, that is conjunction. So P conjunction Q, P disjunction Q, P biconditional, P conditional Q, also P biconditional Q. These all are well-formed formula. Okay. See some example. The proposition, P conjunction Q, disjunction R is a well-formed formula or not? P conjunction Q bracket disjunction R, it is a well-formed formula or not? Yeah, two connectives, conjunction is there, disjunction is there. So conjunction is bracket, so it is applies that order of precedence, it will be true. So no wrong is there. So it is well organized. So it is a well-formed formula. Okay. Then tell me, P negation conjunction Q. Okay. Then P Q disjunction. Then tell me which one is well-formed formula, which one is not well-formed formula. P negation conjunction Q. What does it mean? P negation conjunction Q. You
So
don't know.
both are not well formed.
Yeah, that means see, first one is P negation conjunction Q. What does it mean? It doesn't mean anything. PQ disjunction. So disjunction to what? We don't know. So these type of propositions or compound propositions are not well-formed formulas. Okay. Take one more example. Same example I am showing. P conjunction Q disjunction R. This is a well-formed formula or not? P conjunction Q disjunction R.
So we need to give brackets for that.
Yeah, bracket is not there.
Yes.
If bracket is not there, so it is not a well-formed formula. Because if this is given, one may assume, if this is given, one may assume this may be P conjunction Q disjunction R, this may be P conjunction Q disjunction R. This. So this one or this one, these two are not equivalent. So both cases will be there, different truth values. So that means here you can check P conjunction Q disjunction R is not equivalent to P conjunction Q disjunction R. By truth table you can find it. These two are not equivalent to each other. If they are not equivalent to each other, so one may assume first one may assume the second case. So different truth values come. So it will be not a well-formed formula. That means to make it well-formed formula, we can use the order of precedence that we have studied before. What is order of precedence? To make it well-formed formula, we can use order of precedence. That means if a given formula is not well formed formula, then we can convert it or turn it. We can convert it into a well formed formula by using that order of precedence. Of the connectives or logical operator. That means, see, the last one is P conjunction Q disjunction R. These in the present form, not bracket is there, so that is not a well formed formula. So both these cases, P conjunction Q disjunction R, that is a well formed formula. P conjunction Q disjunction R, that both are well formed formula. But if you are not taking any bracket, that is not a well formed formula. If you are converting into well formed formula, then always use order of precedence. If bracket is not there, which bracket you have to use? See, the second case, P conjunction Q disjunction R, bracket is there, so you don't have to change. If no bracket is there, you are making into that well formed formula. Which part you have to take the bracket? Use the order of precedence. Two connectors, conjunction and disjunction. So conjunction comes first. So take the bracket as conjunction. So P conjunction Q, take the bracket. That will be the using the order of precedence. You can make it well formed formula. Understood or in doubt? Clear or not?
Yes, sir.
Okay. So order of precedence means that we have already seen all the connectives. Which connectives you have to take the bracket first? First is negation, then conjunction, then you can use disjunction, or you can use that exclusive or, then conditional, then biconditional. That is the serial order of that order of precedence. Okay. Then come to functionally complete set of connectives. Set of connectives. It's all the connectives we know, all the that is negation, conjunction, disjunction, exclusive or, and that conditional, biconditional. These are the connectives. The set of connectives functionally complete. That means we'll take a set of connectives. So that will be said to be functionally complete. What are the conditions that we'll see? A set of connectives is said to be functionally complete if there is a condition. See, we take every compound proposition. Every compound proposition can be okay. Every compound proposition can be expressed or expanded, expressed as a logical equivalent proposition. Involving only these logical operators or these connectives.
Sir,
Yeah.
sir, will P union Q without bracket be well formed?
What is tell me what P?
P union Q without bracket.
Yeah, that is also informed. Yeah, no problem. See, for that notation, see, if it is a single like this, P conjunction Q, You may take bracket, no bracket. But after that, that depends upon the other. If after that more logical expressions are there, you have to take that bracket. If only that negation P is there, only that proportionally negation P. That is well defined or well formed, no problem. Only P conditional Q, that is the proposition or P conditional Q. You can write only P conditional Q, no bracket there. Okay.
Yes, sir.
That means see, it will be set of connectives. All the connectives we know, from that we will set of connectives, that is a collection of connectives. Okay, that will set to be functionally complete. That is not what is functionally complete. If you take all the every compound proposition, that must be expressed as any logical equivalent proposition involving only these connectives. That means see, if a set contains one or two or three connectives, so after the remaining connectives, use all these connectives or every compound proposition, that you will find a logical equivalent proposition that can be expressed the connectives that are involved in the set. That means see, one example, the sets negation and another set negation disjunction, and any other set negation conjunction disjunction. These all three sets are functionally complete. See, that means see, I'm going through first. First is what? This set. This set contains which connectives? Connectives in negation and conjunction. That means if let P be a proposition, Q be a proposition, just find P all other connectives. That means P disjunction Q. Write express P disjunction Q in the form of negation and conjunction. P exclusive or Q in the form of negation and conjunction. P conditional Q in the form of negation and conjunction. P biconditional Q in the form of negation and conjunction. That means whatever the present connectives in the set, except that all the remaining connectives, use that every compound proposition that can be expressed in the that can be equivalent to a logical expression involving only the connectives that are present in the set. Got it or not? Okay, see the first example. See the first one. Okay. Just I'm not going to the proof. The set negation and what are the remaining connectives? Remaining connectives. What are these? One is disjunction, one is exclusive or, one is conditional, another is biconditional. That means let P and Q. Okay. So except these are present. That means you have to write. I'm showing only one of them, then you will go through others. Okay. Okay. P disjunction Q. Write this P disjunction Q to an equivalent proposition which contains only negation and conjunction. Tell me, there is any equivalent proposition which contains only negation and conjunction? Use De Morgan's law. That is negation of P disjunction Q. Negation, that is negation law. Then this will be negation of P disjunction Q. What will be this? Use De Morgan's law.
Negation P and Q.
Yeah, negation P and negation Q. So see, the right hand side is a equivalent proposition only containing the connectives. That means it contains only negation and conjunction. Like this, you have to find all. What will be P conditional Q? That will be equivalent to negation P conjunction negation Q. It also contains only negation and conjunction. Like this, you have to find all. What will be P exclusive or Q. Just prove that some connectives. Negation of P biconditional Q. Use some logical expressions that will be also equivalent to negation of P conditional Q, P biconditional Q. Instead of P biconditional Q, we can use P conditional Q and Q conditional P. Okay. Negation of this and this. Use De Morgan's law. What will be this? Use De Morgan's law. What will be this? Negation of P conditional Q. The conjunction is there. That will be disjunction. Negation of Q conditional P. This will be equivalent to same. See, now negation is there, also conditional is there. You have to convert all the logical operator in the form of only negation and conjunction. Then only you can say that functionally complex. Then convert it. Negation of P conditional Q. We can say this P conditional Q, that is negation of P conjunction negation Q. You can use that also. Then what will be this? Negation of P conditional Q, that is negation P disjunction Q. Just wait. You can direct, I have written directly, or you can use this. P conditional Q, we know that P conditional Q, that is equivalent to negation P disjunction Q. So see, P or Q, that is negation of negation P conjunction negation Q. That is same as negation of negation P. That is P. So negation of P conjunction negation Q. So that will be same. Disjunction negation of Q conditional P. So Q P conditional Q, that is equivalent to negation P disjunction Q. Similarly, Q conditional P, that will be same as negation of Q conditional P. That will be negation Q disjunction P. Then again apply the De Morgan's laws. Negation of this negation P disjunction Q. So negation P, that will be P. That will be equivalent to P and negation Q. Disjunction. Negation of negation Q, that is Q and negation P. Finally, we have written this one, this. All are same. Negation is there, conjunction is there, but disjunction is there. So we have to change that disjunction. How to convert it disjunction in the form of conjunction? How to make conjunction in form of disjunction in form of conjunction? Use De Morgan's law. Then how to write? What will be this in the form of conjunction? Okay, see. The first bracket, this one is A. Disjunction, second one is let B. So A and B, see, P disjunction Q. What is this? P disjunction Q, that is same as negation of first and negation of second. You can use this. The first one, that is P conjunction negation Q. Disjunction second one is Q conjunction negation P. That will same as, I am writing again, see. That means we got that P conjunction Q, that will be equivalent to negation of first, that means negation of P conjunction negation Q, and negation of negation Q second, Q conjunction negation Q. So this contains only negation and conjunction. See, that means all the connectives P disjunction Q, there is a equivalent statement in the form of negation and conjunction. P conditional Q in the form of negation and conjunction. P exclusive, that is also in the form of conjunction and negation. Another one is conditional. biconditional. Biconditional already we have written. Negation of P biconditional Q. That is same as all these things. You can write it. P biconditional Q. That is same as negation of, just take the negation both sides. That means this one. Negation of P conjunction negation Q conjunction negation of Q conjunction negation P. This one also contains only negation and conjunction. That means although every compound proposition can be expressed in a equivalent proposition that contains only those connectives that are present in the set, that we have already proved here. Negation, conjunction. So as all of every compound proposition, only these connectives involving to a equivalent proposition involving only these connectives. So we have proved. So from this explanation shows that, or this concludes that, negation and conjunction, this set of connectives is functionally complete. You can see this is a question number. Yeah. That is question number in your exercise 44. That part. That means the set negation and conjunction is functionally complete. So that. Just wait. I'm just writing clearly. Question number 44. To show, what to show? To show that negation set is functionally complete. Yeah, to show this. Let me see. Only connectives are given in the set, that are negation and conjunction. That means you can write here, if there is any compound proposition that contain other than that is given in the set, other than that is negation and conjunction, then what are these connectives? These connectives may be disjunction, these connectives may be conditional, these connectives may be exclusive, or this connective may be biconditional. Then we can replace as follows. Okay, we'll stop here. There is one other part, proportional satisfiability. We'll see in the next class.